Hello, my name is Haolong Li. In this video, I will present you our work, Visual-Inertial Odometry with online calibration of velocity control-based kinematic motion models. Autonomous navigation of robots, such as shown in this image, requires yearly accurate state estimation and also knowledge of the motion model and effect of the control inputs. We propose a kinematic motion model-based visual-inertial odometry for indoor robots with a differential drive that can improve VIO tracking accuracy and also calibrates the kinematic motion model online given control inputs. We develop our method based on an existing visual-inertial odometry method called Basalt. And the VIO is a method that estimates camera pose based on images and IMU information. The estimated states include frame pose, linear velocity, and landmarks, and also the bias of IMU. So if a normal frame hosts enough observations of landmarks, and it will be marked as a keyframe. And VIO usually minimizes the reprojection error that compares the difference between projected landmarks and 2D observations, and the relative pose error that computes the difference between the relative pose of two consecutive frames and the IMU measurements. And it also estimates IMU bias, including gyro bias and accelerometer bias with a random walk model. And this is usually done with a sliding window technique, which means only a fixed number of frames are optimized, and old frames will be marginalized, and their information are saved in this marginalization prior. The major contribution of our work is that we include a kinematic motion model that can provide additional constraint to the VIO. This model is in the robot base frame, and to include such a model, we need to introduce some new states, which are the extrinsic pose between robot base and camera frame, and also model parameters. And since our indoor robot moves on flat ground, we also add a plane model constraint and include the plane parameters. We also assume that the extrinsic pose can change over time, and we model it with a random walk noise. This is an illustration of the motion model we used. It takes the linear and angular velocity control as inputs and drives the robot along an arc. And this can be described as a mapping on SE2. For simplicity, we didn't directly compare the pose difference between the result from the model and the VIO estimates. Instead, we use the inverse kinematics. This inverse kinematics compute velocity estimates from pose and extrinsic poses between two consecutive frames. Then we compare the difference between the estimated velocity and control inputs. But a problem arises from here is that the real action of the robots differs from the received control commands due to delay and the properties of the underlying low-level controller, which translates velocity inputs into wheel speed. Thus, we first compute an effective control and compare with it. The effective control is estimated from a window of most recent 3 control inputs. We average the recent control inputs with the RBF kernel. This RBF kernel depends on the time difference between the control inputs with the first frame of the 2 consecutive frames. And we optimize the RBF parameters together with other VIO states. The image here shows 2 different groups of the parameters, and as we can see, different parameters lead to different shapes of the RBF kernel, and thus, by optimizing for the kernel parameters, we can adapt the value of the effective control. We evaluate our methods with real-world experiments. Here is the robot setup. We use the Kabuki TotoBot and equipped it with a T265 stereo fisheye camera. And here, the image on top is an example of the qualitative result, and our method shows a smaller drift compared to the original VIO at the corners. And below is a table of the summary of the quantitative evaluation, and again, our method achieves smaller drift compared to the original one. We also validate our online calibration by evaluating the prediction. The prediction is computed based on the forward kinematics using the effective control with the optimized RBF parameters. We compare our method with other naive baselines. The first one uses the result of an uncalibrated RBF kernel. The second one takes the mean value of the most recent 3 controls. And the last one directly takes the latest control for prediction. We perform the prediction on different time horizons, and our method shows smaller error comparing to the baseline methods. On the right is a qualitative example of the prediction from trajectory begin to the end. Our method also shows relatively smaller drifts. Okay, that's all of this presentation. If you have any questions, feel free to reach out. Thank you.